I never imagined in my wildest dreams that molten metal could explode out of the pan that I'm cooking. So to turn down the heat, I grab the pan, I turn it to maybe like a 30 or 45 degree angle, and molten hot metal exploded on me. It exploded out of my pan, all over my stove, and all over the floor, all of these metal bits.
Hey there, good morning. I totally know what happened there. I'm pretty sure I know exactly what happened, and you're probably not going to like this. First of all, I'm very sorry that that happened to you. It is not fun getting hot, burning molten metal on your skin. I do it pretty routinely, but I signed up for it when I became a welder. But when you're a normal person, usually getting like surprise molten metal on you isn't usual. Another piece of information you might want to know is that that's aluminum. I can tell by contextual clues with the temperatures that you're using there on the stove, but also the way it looks. That is textbook cast aluminum. It's not stainless steel, because when stainless steel reaches temperatures that are hot enough to melt it, which there is in all likelihood no possible way that that was stainless steel melting. Stainless steel without a shielding gas of some kind, when it becomes molten, will become crystalline and black. And the surface of the pan looks like it may have reached the temperature, but that molten stuff, that's aluminum, and aluminum is really great for doing casting. If you wanted to build a thing out of molten aluminum, you could without much of a flux or a shielding gas, and it just looks like it came out of your pan instead. What you have there, by my best guess, is something made by Cuisinart, because that's in your tag. You've got a multi-clad triple ply stainless pan, which is much like the ones that I've got in my house. It means you've got a stainless steel outside and an aluminum core. If it were completely stainless steel, this thing would be very, very heavy. Aluminum makes it lighter to work with. You know, cast iron is super heavy too, because it's solid cast. But aluminum is also a much better, it has much better thermal conductivity than stainless steel does. Stainless steel tends to kind of leave hot spots, where aluminum will heat the bottom of your pan evenly. And it's for many reasons. They use aluminum inside of these pans instead of having them be solid stainless. It's aluminum. You can almost hear it. They sandwich it together by welding processes like expulsion welding, or I can't remember. But there are other ways of fusing dissimilar materials together that are only microns thick. They're very strong, but they're also very thin, and they can delaminate. I'll get to that. Actually, what we've got here with the softer, lower temperature material inside of the pan, covered with a shell of an outside harder, high temperature material, is exactly what this is. I made a video before of an experiment we did in a chem class once, which was to melt the zinc inside of a penny before we melted the copper husk. In 1982, they stopped making pennies out of solid copper because it just wasn't feasible, economically feasible anymore. And so now we have got a copper jacket around zinc. If you were to take a file, you could nick that and see the zinc inside. If you were to take a grinder, you could nick this and see the aluminum inside. By the numbers, the stainless steel on the outside of this pan melts at about 25 to 2800 degrees Fahrenheit, while the aluminum inside of it melts at about 1200 Fahrenheit. That's a difference of about 1400 degrees. 1400 degree difference between the melting points in the two layers in here. Same with a penny. Pure copper melts at about 2000 degrees, and zinc melts at about 800 degrees, leaving a difference of about 1200 degrees. So all that is just to say, these are both sandwiches with goopy insides once they reach a certain high temperature, with an outside that's like a shell. Like an M&M or a Reese's. If you've ever had candy and you can pinch them and the chocolate goops out, but the shell stays sugary, that's exactly what these are too, just at a higher scale. The other part of this puzzle is to know how electric stoves work. When you turn the dial and you set the temperature to where you want it to be, it's not exactly a temperature setting. That's why they don't have temperatures right on the dial like they do on an oven. Most electric stoves in houses only reach about 700 degrees, but there are caveats to that. That's just the average of what it settles at under a normal thermal load. It's just a rough, steady state, and it's not set as a maximum by a thermostat anywhere. This means that the stove does the best job it can trying to sense what you're trying to do by sensing the entire bottom of the surface of this pan and whatever's inside of it. This is a big heat sink. Whatever you put in to cook is also a heat sink. A sink is anything that takes away. An energy sink could be your hobby, your job, your kids working out. A heat sink is anything that takes the heat away. My hands are currently acting as a heat sink to my hot mug of beverage. And the first thing I want to mention is that this pan is overheated. The picture that you showed, you know, the video that you showed when that molten material actually shot out of the pan, the camera pans over to the top of that and it's glowing red. Man, that's a great way to destroy your cookware, and it's not going to be covered under warranty after that, because after that you get deformations. And if that bulges or warts, you no longer have a smooth, even contact surface on whatever type of stovetop that you're using. And that water droplet test that sometimes you see in cooking shows or read about in blogs, I really don't like, unless you're kind of a seasoned chef and you know a little bit more about thermal conductivity and materials in cooking and how heat affects metal. That's why I would have any new welder start on oxy fuel, because the very first thing you need to be able to do is see how heat affects metal, because you can back off when you see it getting too hot. And that's kind of what happened in this case too, only it was cooking. There are so many parallels and analogies between cooking and welding because it's all heat control. That's what happened here. Some people will tell you to check the temperature of a pan by throwing a little bit of water. It's supposed to be just a little minimal water drop that you kind of flick onto the pan. If the drop sits there and starts to steam, you know, it's not hot enough yet. And if it actually skims across the surface, it's way too hot. You want to look for a drop that bounces off of the pan, because what's happening is that little water drop is making contact with the surface of the pan and creating a little water vapor, a little cushion, and it poofs the water bubble, the droplet up, and then it lands again, and then poofs, it vaporizes. And so you're looking for that water droplet to dance over the top of the pan on that cloud, that little springy surface of water vapor. That's the Leidenfrost effect, and it was developed as a marketing thing in the the 70s or so, when we still had traveling salesmen and commercials, and, you know, trying to get people, especially women, to buy the product. And they would flick a little water in the pan to say, see, this is how you know that it's ready to cook with, because the water dances across the pan. It's something that we can still use. It's still useful, but nowhere near as useful, I would say, as a little bit of experience in cooking first. Let's put it this way. I didn't teach it to my kids. I taught it to them incidentally. So as we were cooking and we throw a little water in the pan, you know, teaching them the difference between oil in a pan, water in a pan, how oil behaves, how water behaves. You don't mix the two of them. Throw a little water in there, it goes tss, and like immediately steams. It's way too hot. Take it right off the heat, turn off, take the pan off, turn the heat off, take it outside. By the way, the Leidenfrost effect only happens at about 400 degrees, and to me, that's way too hot to be cooking eggs. I cook my eggs at under 200 degrees because I like a soft egg. So the water droplet test is only to be used at sane temperatures with no delay in cooking. You don't just like start heating your pan up and then walk away and then come back and throw water at it. That's a really bad plan. So this whole situation kind of set up the conditions for this to happen, the molten material to come out. You said when you were cooking, you also tipped your pan up on an angle, which probably means there was less contact and there was poor heat transfer, because everything was being concentrated. All the heat, all the energy coming off of that coil was being concentrated into one point, likely down here. Locally, this one little area is being overheated as heat isn't being taken away fast enough. And that coil keeps trying to heat things until the radiative loss balances out. Things balance out again. Like I said, it was an empty pan, so that means there was less of a heat sink. And you're concentrating heat in a fraction of the material. You have no equilibrium anymore. And unfortunately for this situation, if you go and you read how to use these pans, you know, the instructions that nobody looks at, it warns against all of this. Stovetop coils don't sense a temperature. They just keep dumping wattage in until the coil glows at the predetermined area on the knob. Back to the metallurgy of what probably happened in your pan. There had to have been some sort of a breach in the stainless steel, I think. Like, either the pan had been overheated once before and there was some bowing and warping in it to where it was uneven contact surface with the coil, or it had been overheated to the point where the stainless was no longer stainless anymore. The chromium in it was irrelevant. Stainless steel is amazing in that it resists oxidation and rusting and corrosion and pitting, but that is completely lost when you get the temperatures up too high. That's why you have to be very careful when you weld it. Control your heat. When you do a little stainless weld bead, you want to see that like salmon rainbow color over the top of it. When you lose your shielding gas when you're TIG welding on stainless, you will know immediately, because you see black, you see smoke, and you see like black sugar crystals, and that happens on the backside of a stainless weld too if you don't back purge with a shielding gas like argon. So there may have been a weak spot in the stainless steel already to begin with in this scenario we're talking about. It could have been a manufacturing defect. It's just my guess that it likely was not. So the aluminum inside of our sandwich was starting to heat up and melt and deform and bend before it became a liquid, and aluminum also expands a lot faster than stainless steel does. So stainless steel not only did not expand, but it was resisting the expansion of the aluminum inside of it. So that's another way I suppose it could happen, was as the pressure is building from the expansion of the aluminum as it's being superheated. Also, if there's any kind of a void where like water could have gotten into, I think at these temperatures, the water vapor, well, if the water vapor could have gotten trapped in the laminating layers as all of this is happening, and then it found a way out, it'd be a lot like popcorn. That's how popcorn works. The moisture inside of the kernel is a sealed vessel with all of the corn meat, the kernel meat inside of it, and as that gets heated and superheated, that pressure builds up as like a balloon ready to burst, and then bang, it does, but it pops up into a delicious snack, not molten material on your foot while you're trying to cook. That foldy, melty aluminum started to liquefy, it started to fill any available spaces, and it would have gone to the weakest point in the stainless steel, and if probably just enough compression in there to burst through. at a certain point. And I'm guessing that that certain point was the point of heat, the point of contact with this on the burner where it was the hottest, where it would have been weakest. I'm also very surprised that you didn't smell smoke before this. Either you clean your pans very well or you don't cook with oil very much, because I feel like I would have smelled like old burning oil or something going on far before the material blasted out. Because again, I saw that red glowing on your pan. That pan was left unattended, darling. I don't know how long it was standing there, but that's a bad plan. Just for safety's sake of anyone who sees your video or has seen that in their lifetime, be careful with the glowing pan, not just because it's glowing in front of you, but when you go to use that pan again, you've already deformed the pan and you're going to make it more likely to happen again. So in short, it is my somewhat internet expert opinion that the failure was caused by user technique over manufactured defect. It likely overheated, causing the aluminum to melt. Tipping it up on a single point caused superheating at one point in the pan, causing a failure. Visible red glow confirms that the pan was being used at excessive temperatures, and that would be consistent with severe overheat to delamination temperatures. The penny trick. If anyone wants to see me do the penny trick again, I can. You can get the inside of the penny to come outside with a torch. You just hold it with forceps or side cutters, needle nose pliers of some kind, and then you pass it over a torch. I think you can use a Bernzomatic. That's what my instructor did. Or you just heat it with a torch. You don't want it red hot. You don't want to melt that copper jacket, that thin copper jacket on the outside of it. You just get it really hot, nice and hot, and then at the very last minute, you have a coffee can full of like water that you're going to slam it down on. At the very last minute, you heat the bottom of it, superheat the bottom of it, and then go slam. And all of that molten material, the zinc inside of it, which melts at a lower temperature than the outside copper jacket does, drops out of the bottom, and you can pick it out of the bottom of the water. And that's exactly what your stovetop looked like to me. I don't know where you go from here other than to please be very careful. Throw the pan away. Don't do that again with any of your other pans. If it were me, I would not do that water thing. Just start cooking with your pans more. Just put your pan on the stove and always use medium. Always use medium. The only time you should really be using high, in my experience, the way I cook, is if you're searing. The temperatures we're talking about for dancing water across a pan, 400 degrees, that's like for a good sear. If you want to throw a steak on for like a minute or two and then finish it off on the grill or at a lower temp or in the oven, you could use it for that. But stick to medium temperatures for like everything you cook, especially eggs, man. I could cook them over low, medium heat. Rubbery eggs. Ugh. If you ever get the egg ick, it's likely because you're eating overcooked eggs. That's my 2 cents on it. My 1 cent.